Ta-da! You made it. This is the absolute maximum, I suppose, of your calculus experience, at least in Calculus 1. And it is the fundamental theorem of calculus, part 1. One of the most important and all-encompassing theorems that you'll see around in any field. And it'll be the theorem that ties together the idea of the derivative and this idea we've been developing up until now of the integral. So what is this all about? Well, as we go through, we got some examples, and it's actually a pretty quick theorem to apply, right? But you really got to know the basis behind it. So we're going to start with that. So let's pretend like you're driving in a car, and you model your velocity with this function v of t equals 15t, all right, which is measured in miles per hour. So for example, your speed at time 2 is 30 miles per hour. Let's say that it's in hours, which is kind of weird, but that's okay. We'll go with it. Your speed at time 3 is 45 miles per hour, and so on. So there's this nice line that represents your velocity at a certain time. So what we can do is we can calculate how far you've traveled in certain intervals. So from time equals 0 to time equal to 0.99. And all I did, all right, in order to calculate this is realize that I've got this nice little function right here, which forms a triangle between the function and the x-axis. So if I were to find out what your distance traveled is from time 0 to time 1, right, the area under this curve is what gives us that amount, right? So for example, at time 0, you started out at 0 miles that you've traveled, but then by time 1, it appears that you've traveled quite a bit. In fact, you traveled to the point where you're actually going 15 miles per hour. And so if we were to actually go through and calculate the area under this curve, as we've already kind of discussed, has to do with the total amount that you've gone, all right, we find out that that area is 7.485 miles when we go up to 0.99. If we find the area from 0 to 1, that's the area under a velocity curve, all right, which is 7.5 miles. If I go all the way out to 2, all right, you see that I've got this nice little triangle here with a base of 2, a height of 30, and it ends up being 30 miles because that's the area of this triangle. And we can do the same all the way up to 2.001. All right, we talked about that before. What's that have to do with anything? Well, if we want to find the rate of change of our distance at time 1, you notice that I just set up a nice little situation where I've got a difference quotient. So I can say s of 1 minus s of 0.999 over 1 minus 0.99. And we actually could solve this, all right, and find out how far, or excuse me, how much, what our rate of change is of our distance at time 1. And so when I work this out, I get 15 miles per hour. If I do the same right around time equal to 2, like s of 2.001 minus s of 2 divided by 2.001 minus 2, I get 30 miles per hour. Well, wait, what's the deal with that? Well, the rate of change of our distance was just what we get when we plug in time 1 into our velocity function, or time 2 into our velocity function. So in other words, when we integrated, we found the area under this curve, and then when we found the rate of change of that area, all right, we came back to our velocity. So some other things to notice about this is the integral from 0 to 2 of v of t is equal to 30. All right, we calculated that. That was the area underneath this triangle. But also notice that if I were to find the antiderivative of this, I would get 7.5t squared. And then plugging in 2 and 0 also gives me 30. And I kind of worked that out right here. So in other words, the integral from 0 to 2 of v of t dt is its antiderivative at 2 minus its antiderivative at 0. In other words, position is the antiderivative of velocity. So we got 30 in both cases. So somehow there's this connection that's floating out there between the area under a curve and the antiderivative, all right, along with this derivative idea. Oh, here's the idea. Let the integral from 0 to x of v of t dt represent a displacement after time x. For example, the integral from 0 to 4 would be our displacement after time 4. How far have we traveled in total? So as we just saw, the derivative of this integral, right, of this integral of the area underneath the velocity curve got us back to velocity. And in fact, what it gave us was the velocity at that certain time when we stopped accumulating. So in the previous slide, we got the velocity at time 1 and velocity at time 2. all right? And if we were stopping at time 4, we would find the velocity at time 4. So the derivative with respect to x of this integral from 0 to x of v of t dt is just v of x. It's whatever your velocity is at time 4, or at time x, I should say. So the idea is we're finding the area under this curve, and then we want to find the rate of change of that area accumulation. And we end up with just the integrand with the upper limit plugged in. We give this a name. We call it the integral from a to x of f of x dx is called what's called an accumulation function. We're accumulating area underneath the curve. Now, often, and we'll pause right here. I'll show you the actual theorem in just a minute. But we use a t right here as f of t and dt. All right, and that's going to be what's called a dummy variable. It's not wrong to call it this, right? But we're going to kind of not get our variables mixed up, and we'll see that in the theorem in just a second. So all this leads to a nice little theorem, which we're going to call Ftc Part 1. And it states if f is continuous on a closed interval a to b, then capital F of x, which is the integral from a to x of f of t dt, so this is the area under the curve, starting at a and stopping at some point x, which we're going to say is a variable, of f of t dt, all right, that function is continuous on the closed interval a to b, differentiable on the open interval a to b, and is what we're going to call an antiderivative on a to b. So in other words, the derivative of this capital F is just f of x. So it's the integrand with x plugged into it, right? And it seems like this is like no big deal. What's the deal? All right, but the idea is that we know how to find an antiderivative, and the derivative of the antiderivative is the original function. All right, and this particularly applies for what we call accumulation functions when we're trying to find out area under a curve. What's the upshot of this? Well, the upshot is that you got a really actual easy night as far as what you're trying to calculate here. So here's an example. Let's say we want to accumulate the area from 0 to x underneath the function square root of 1 plus t squared dt. And what we say is the derivative of that area function, this accumulation function, is just the integrand with the upper limit plugged in. So when we take the integral, it's like we're going up a floor on the elevator, all right? We're finding another level, the second level of our function chain. But then when we take the derivative, we get back to down to the function that was originally there. So this derivative of this accumulation integral is just the square root of 1 plus x squared. Notice it's just the integrand with x plugged in. That's it, right? The idea is simple. When we integrate, we go up a level. When we take the derivative, we go down a level. And all we get, we're changed a little bit. We have our new limit plugged in here, but we get the same function that's inside our integral. Why are we ignoring the lower limit, by the way? Why 0? Well, this part actually doesn't matter, the 0. It's the x, the variable that matters in this case. So think about what we're doing. The rate of change that we're accumulating doesn't really depend on where we start, but where we currently are. So if we think back to the velocity example, all right, it doesn't matter what your velocity was at time 0. You want to find your velocity at time x, whatever x you're given. Here's another example. The derivative with respect to x of 1 plus x, derivative with respect to x of the integral from 1 to x squared of cosine of t dt. This is another case where it's time for the chain rule. We only know by this FTC part 1 how to take the derivative of an accumulation function if the upper limit is just x. So what do? Well, at least say, well, I wonder if we just replace x with u equal to x squared. And so now I've got this new integral, all right, y is equal to the integral from 1 to u of cosine of t dt. So by the chain rule, that means dy dx is equal to dy du times du dx. So the whole idea of dy du is taking the derivative of this integral with respect to u is just the integrand with u plugged in. So we get a cosine of u. But then what is du dx? Well, remember when we did substitution just a little bit ago, all right, and we want to take the derivative of u with respect to x, we're going to get a 2x. All right, so overall, our derivative is cosine of u times 2x. And u, of course, is x squared, so we plug that in, and we get 2x cosine of x squared. So I'm showing you like kind of the theory behind it, but actually it's really quite simple. All you're doing is you're plugging in x squared, and then you're multiplying by the derivative of 2x because of the chain rule. Right? Think of this x squared as like an inside function here. All right, so derivative with respect to x of the integral from x to the fourth to 1 of secant of t dt. So notice our FTC talked all about taking the derivative of an integral with a variable at the top. Well, how can we fix that? Well, all we got to do is change the order of the limits. All right, so we'll make this negative d dx of the integral from 1 to x to the fourth of secant of t dt. All right, so therefore our answer is what we get when we plug in x to the fourth into secant, that's our integrand, and then times the derivative of x to the fourth, which is 4x cubed with the negative out front. So our answer is negative 4x cubed secant of x to the fourth. What do we do when we have variables in our upper and lower limits? Well, remember that the integral from a to b of f of x dx is the integral from 0 to b all the way to b of f of x dx minus the integral from 0 to a. So you take away the area that goes all the way up till a of f of x dx. In other words, this derivative is the derivative of the integral from 0 to x squared of 1 over t plus e to the t dt minus the integral from 0 to 2x of 1 over t plus e to the t dt. All right, so we take away the area that goes from 0 to 2x. All right, so when we take the derivative, all right, we can plug in x squared in for t. So we get 1 over 2 plus e to the x squared times the derivative of x squared, which is 2x, minus 2 times 1 over 2 plus 2e to the 2x. So we plug in 2x in for t, and the derivative of 2x is 2. So in other words, we're plugging in our upper limit, we're plugging in our lower limit. All right, plugged in an x squared, plugged in a 2x, and made sure to take the derivatives of both those upper limits. Okay, so as we go on, let's kind of do a little quick review of what this accumulation function is all about. What are we actually finding here? So we say capital F of x is equal to the integral from 2 to the x, 2 to x of f of t dt. And we want to answer the following about f of x. So what is this actually asking us to do? Well, it's saying if x is equal to 0, I want to find the integral from 2 to 0 of f of t dt. And that's just the area underneath this curve. All right, so I want you to notice the area from 2 to 0 is the area of this triangle, all right, moving backwards. So we're going from 2 to 0. So the area of the triangle is 2, and so the area that we get with the integral is negative 2. When we go from 2 to 1, all right, that's the area of this little tiny triangle right here, and that area is negative 1/2 because we're going backwards from 2 to 1 with an area triangle of negative of 1/2. And since we're moving backwards, that makes the integral negative. The integral from 2 to 2, all right, of f of t dt is just 0. That's saying find no area between 2 and 2. And then all these other areas we actually find by finding the areas of either circles or triangles or circles that are semicircles that are below the axis. But the connection I want to make here is that we're actually finding areas. And the accumulation of our area is this function that we've created that's changing as x changes. All right. So the whole idea of FTC is when you take the derivative of this accumulation function, that rate of change of the area that we find is little f of x. It's actually the function itself. So among other things, as you can notice, all right, the idea is when we get to 6, we've accumulated the most area that we can. And part of the reason that that is, and there's more on this later on in the unit, all right, when we get to 6, we've accumulated all the positive area that we possibly can. So we have a relative maximum as far as the amount of area that we have. And as you can see that from our numbers, our areas actually start going down as we go along. Okay, the final thing that we've got, express the antiderivative capital F of x as satisfying the given initial condition as an integral. So the whole point of this is, if we have a function like little f of x, which is equal to the root of x squared plus 1, and we know where to start, we can actually create an antiderivative. We don't need to go through the whole process of a reverse power rule and all that. The antiderivative is always this accumulation integral, taking into account what your initial condition is. So we can create an integral with our starting x value as the x value of our initial condition, the integral from 2 to x, of the cube root of t squared plus 1 dt. All right, so this antiderivative is just what the FTC tells us to do. And notice if I add 1 to this, now the integral from 2 to 2 is going to be 0, and adding 1 gets us our initial condition. In summary, that's a powerful theorem. The accumulation function is a hidden derivative. And don't call to come back. The chain rule makes a reappearance, and so do all those definite integral rules. Believe me, we're going to talk about this in class, and we'll see you then.